So I guess we're going to start 15.7, and we have one more example. We want to do this. We want to show how triple integrals work with spherical coordinates. That's what I want to do. I want to show how triple integrals work with spherical coordinates. And so I'm basically doing, let me list this. This is problem 47. And so they give me the transformation. You might remember that what 15.7 is all about, okay? So let me say a couple things about it. It's all about change of variables. In higher dimensions, let's say. That's what it's all about. And so in general, what we're going to do is, let's say we're going to do some triple integral over d, say dz, dy, dx. And should I put some function here? I guess I'll put f here, right? When I say f, f is a function of what? X, y, z, right? So we're going to integrate it, right? So what I'd like to do is I'd like to show you how we change the x, y, z world. And do you remember the well, okay, so we want to rewrite this again as a triple integral over d. But what are the variables we're going to use? Well, here's what you need to know. You need to know that basically the transformation that goes from from spherical back to, this is rectangular. The transformation is given as follows. X is equal to, and this is given in problem 47. Do you guys remember what that means? That's rho. That's the Greek letter R. The book's rho is better than mine. Looks a little bit like a P. Sorry about that. Rho times the sine of, that's not so good. Try again, Paul. Why am I having trouble today with that? I'm trying to write phi. I think like this is how I usually write it. The sine of phi times the cosine of theta. So x is, here, let's try again so we get it nice and neat. Sorry. X is rho sine of phi cosine theta. Y is rho times the sine of phi times the sine of theta. Okay. By the way, this shouldn't surprise you too much. You guys, if I took away phi, for example, if I said that phi is 0, do you remember what phi is on the picture?
It's the angle from the z-axis.
From the z-axis going down, right? That's phi. So, let's see. If you didn't have phi, if phi were 0, you'd have the sine of 0 is 0. All of a sudden I could say, oh, my x and y, right, are given by r, that that rho cosine phi theta and rho sine theta. What kind of coordinates do I have now, guys? Polar, right? So if there were no z coordinate, these would just be polar coordinates. But there is a z, and that's why you need to measure kind of angle from the z-axis. And it turns out that z is equal to, and I think this is what I messed up last time, right? Z is equal to rho times the cosine of that phi. Okay? And so what we're supposed to do here is kind of show, again, how triple integrals work, is what I would say. What they say to do is just compute the Jacobian. So what I have, for instance, is I could put, x rho, x phi, and x theta. And then I have y rho, y phi, and y theta, and z rho, and z phi, and z theta. So there's 9 partial derivatives we have to compute, right? And we have to take the determinant. And I explained to you guys already how to take the determinant of a 3 by 3 matrix. We've done that. We talked about it last time. You're going to see an example now. Okay? So again, I guess there's some computations to do here, so let's do them. Let's see. When we go through this, so we're going to have the determinant of, in the first row here, I want x rho. All right, well, here's x, right? So if you take the derivative with respect to rho, you just get the sine of phi times the cosine of theta, right? Actually, the rho's are really simple, right? So same thing here. When you take the derivative, y rho would be sine phi, sine theta, and z rho would be what? Cosine phi. So I guess the first column was easy. The second column, I'm taking derivatives with respect to phi. Oh, well that's easy, because what's the derivative of sine phi? Cosine phi, right? And everything else is a constant, so we'll just write it the same. It's going to be rho cosine phi cosine theta. This one is rho cosine phi sine theta. And this one is negative sine. So negative rho sine of phi. Yeah? And now for the last piece, here, I'll do the last one. Right? 0. But there are no thetas in the z function. And this top one would be negative rho sine phi cosine theta. Right? Nope. Made a mistake. I caught it though. That negative was correct. But what was I taking the derivative with respect to theta? So this became what? Sine of theta. Okay. And then the next one should be positive rho sine phi. That becomes a cosine theta. So I need to take the determinant of this matrix. And what I do is I pick a row or a column and I move across, finding what are called the cofactors and following this checkerboard pattern. Right? So I need to pick a row or a column to move across. And I choose row 3. Why? Because there's a 0 there. I guess I could have chosen column 3 also. But I chose row 3 because these things are pretty nice. Nice, easy things to do. Right? So I'm going to say that this equals, let me work this out now. When I get here, it's a positive. Positive cosine phi times the determinant of a 2 by 2 matrix. What's the 2 by 2 matrix? It's top corner. Yeah, I'll put it in kind of brown here. And I'll just say it's that stuff. So maybe I should write it all out. the determinant of rho cosine phi cosine theta. The other part is rho cosine phi sine theta. And this is minus rho sine phi sine theta and rho sine phi cosine theta. Okay? So I have to do this, and then moving across, I need to subtract. Now look, we have negative rho sine phi times the determinant of what matrix this time? See, the way I got the Brown matrix was when you're at a certain spot, you delete the row and column that you're in. Yeah, so it's going to be outside, right? Let me be careful about this. I mean, it's going to have to be bigger.
Can you move it down a little?
Oh, yeah, sorry. Let's show that. So what we're going to do, I'm here, right? So I delete that bottom row and I delete this middle piece. And so what goes in here, I guess, it's negative rho sine phi times. The first column is going to be sine phi cosine theta and sine phi sine theta, right? That's the first column. And the second column is, again, this third row. It's third column, negative rho sine phi sine theta and rho sine phi cosine theta. There we go. So after that equal sign, there's a big mess. Let's see if I can simplify. Here we go. This equals cosine of phi times what? Let me do the determinant of the Brown matrix. We get rho squared. It is what it is. We had someone come in here once about that, and they couldn't help. All right, rho squared. And when you multiply these together, you can see we're going to get sine phi cosine phi and then cosine squared theta, right? When I multiply this one by that one. How many are with me? Not many. I'm going to pause and catch people up, and then we'll continue the recording. So the cosine of phi times, we're doing that and that, right? So we get rho squared sine phi cosine squared theta. Matthew.
Not with what you're doing right now, but shouldn't the equal sign in front of that be a plus then?
This equals?
Yeah, no, down a couple spaces.
This equals?
Yes.
No. Because what I'm saying is this...
Oh, because it's zero. Never mind.
Because there's a zero. That's why there's only two terms instead of three. So let's see, I get cosine phi times this stuff. And then I can write, oh wait, I didn't do this. Minus, and now when you do this, you get negative rho squared sine phi cosine phi, and then what? Would it be sine squared theta? Right? So all that times cosine of phi. Okay. Moving on. Plus, from the other term, rho sine of phi times what? Times some big mess. Let's take the determinant of that 2 by 2. Looks to me like I get rho sine squared phi, right? Sine phi times sine phi. Oh, look at that. Cosine squared theta. This one's a little nicer, this matrix. And then what do you get? Minus negative rho sine squared phi sine squared theta. Okay? So, continuing this mess, right? I guess I have cosine phi times all this stuff. Now, you'll notice, though, the minus minus, of course, is going to become what? Positive. And then I'm going to factor out all the common factors I see. Like I see rho squared, right? And then I see, what else is common? Sine phi and cosine phi, yep. And so the only thing you have left is cosine squared theta plus sine squared theta, which is really nice, because what's that equal? That equals 1. So this is going to simplify significantly in a moment. And if you play the same game with the stuff after rho sine phi, let's do that. So we're going to write plus rho sine phi, and let's take out common factors. So what common factors do I have? Well, I have rho and sine squared phi, and then same thing happens, right? We get what's left over is cosine squared theta plus sine squared theta, right? How many are with me up to here? That's better percentage. I like it. Okay, so if I just continue on from here, of course these things are ones, so I don't need to write those parentheses things down anymore. What I'm trying to do next, guys, is, you see that plus sign? I want to take those two terms and I want to take out, after my equals, I want to write down what's common. So I guess we kind of ignore these because those are ones. What's common to this term and that term? Well, rho squared, right, is common to both. Is there anything else you see common to both? I see a sine of phi here and here, right? Sine of phi. So what's left besides that? Well, if you're tallying at home, keeping score at home, like you will tonight for the first tribe game, cosine squared phi plus sine squared phi. And so we have just computed that the Jacobian ends up equaling simply rho squared sine of phi. Okay? What does that mean? It means the following. You guys, you were asking me about Chapter 15, Section 3 on polar coordinates. And what I told you was, if you have a double integral f of xy dA over some region, we told you that that equals same double integral, but you can change to some function of r and theta, polar coordinates, as long as you replace the dA with what? R dr d theta. I guess the point was, this R is the Jacobian of some 2 by 2 matrix. Okay? Well, you guys also asked me today to do an example of a